So, congratulations for making it to Chapter 3. And once we've gotten here to Chapter 3, that means you've graduated through Chapters 1 and 2, and you receive a certificate. And the certificate is your very own periodic table. All right. So you need to have a periodic table so that we can reference things and talk about things and learn how to use this table. If you don't have one, we have it available on the website, where it's going to be a Word doc or a PDF that you print up, and it's going to have some tables on the back as well. We're not going to use those tables for a little bit, but we'll get to them eventually. And again, this nice periodic table, you'll always want to have it available when we're having our conversations, because it will, in the olden days, they used to say, okay, here's the periodic table, memorize every element. Memorize every element, memorize its mass, memorize its location and its name and its symbol, right? But I feel that memorizing is good and has a place, but it's the kind of memory that doesn't stick always. Sometimes it does, but sometimes it doesn't. But the memory that it always sticks is the one that you're constantly being reminded of, because you need to use it over and over again. So the periodic table, I want that memory to come to you that way, so that you can't forget it, because you just use it so much. Now, I can't force you to use it if you're on the other side of the computer, so you're going to have to kind of keep it on yourself to always have it. And when I say, hey, what's it say here on the periodic table, you got to look. You got to look and try to have it available. I'll try to bring it up too when I ask questions about it here, but recognize that our connection and our use of the periodic table is a critical component to help us understand the world around us, matter and the world around us. All right, the title, Elements, Compounds in the Periodic Table, is nice because we've already talked about elements. We've already talked about compounds and the periodic table. Now we're just going to kind of dig deeper into an understanding of these principles. Okay. Our understanding of the atom that we've already discussed is that we have an atom with a nucleus, and in the nucleus we have neutrons and protons. Again, this should be pretty much review. And then outside of the nucleus we have our electrons. So our three kinds of subatomic particles are our electrons, our neutrons, and our protons. Okay? And we can see here the difference in the mass between our electrons and our protons. Electrons are more than 1,000 times smaller. Right? So 10 to the minus 24 here for the mass of a proton, 1.6 times 10 to the minus 24. That means you have to move the decimal place over 24 times. That would be then 0 point with 23 zeros and then a 1,672,64. Right? That would be the mass in grams of a proton. But for an electron, you have 27 zeros and then the 9109. Right? So electrons' masses the mass of an electron is always going to be more than 1,000 times smaller than that of a proton. Whereas the mass of a neutron is almost identical to the mass of a proton. The charges on these, again, kind of review, but electrons are negatively charged, protons are positively charged, and neutrons are neutral. Okay, no charge on the neutrons. All right. We have ways of writing the elements, right? We have our elemental symbols, which we've seen and are familiar with. And I'm going to introduce to you a little bit more about ways that we can kind of convey information about the number of protons, neutrons, and electrons in an element It's simply by how we write that elemental symbol. Well, or the numbers that we write around it. For example, if I write the symbol C, that's carbon. So we can look on our periodic table and see, okay, that's carbon there. And that number 6 up there, if we had a periodic table, will remind us that, do you remember what that number is? What's that number, number 6?
6 denotes the number of protons?
That's right, 6 protons, 6 positively charged subatomic particles, protons, in the nucleus. Now, if you know your audience is not going to have a periodic table, then you can write a 6 kind of in front, in a subscript format, in front of your elemental symbol. So this 6 helps people remember that might not have the periodic table that there's 6 protons. Okay? And to test our understanding of this principle, we can, for example, write, here is some element, and it says 15 right here. So what element does that represent?
Let's see. We're so close. So that's so I see the S. It's
well, it's 15, and what is that
sulfur,
15?
right?
No,
No,
sulfur
no.
is the 16.
That's so P.
Phosphorus.
Oh, phosphorus. Okay, yeah, I'm just having a hard time getting the.
Still a little small, huh?
Yeah.
Okay. All right. So that position on the element, the 15 there, or the subscript in front on the bottom, is telling us the number of protons. And again, it's useful for people who might not have a periodic table around and that don't have the elements memorized, right? Okay.
Hey, Dan, can we pause for...
So that box on the periodic table, like we mentioned, we have our elemental symbol, and we have above it, and not all periodic tables are formatted the exact same way, so sometimes it's above it, sometimes it's over to the left, or maybe even over to the right. But the number indicates the number of protons. Now, if we want to tell somebody about the number of neutrons that are in this atom, so we have 15 here, which told us the number of protons. If we want to tell somebody the number of neutrons, the tool that we have available to us, there's not a spot to write exactly the number of neutrons. But we do have a tool that we can help people know the sum of the number of protons and neutrons. So that number up there, called the mass number, is the sum of protons and neutrons. All right? So in a way, we can tell people, or not in a way, we actually can identify, help people know the number of protons. They'll have to do a little subtraction, but if I say that the sum of the protons and neutrons, or the mass number, is 30, and the 15 is here available to them, they can know that there are 15 neutrons, and in this case as well. So let's choose another example. Here is what we call carbon 13. Carbon 13. And you don't call it carbon 6 because somebody knows the periodic table or knows the elements, then they already know how many protons there are. But you will call it carbon 13, for example, or you will use the numbers to help people know the number of protons plus neutrons. Okay? So carbon 13, how many neutrons is in an atom of carbon 13?
7.
7, right? Very good. So our mass number there helps us know how many protons and neutrons are in a given element. Very good. Now, on the periodic table, this mass number is, is not always a whole number, or is never a whole number. All right? Because this mass number, in this case it's 55.847, isn't the mass of every single iron atom, it's the average mass of a collection of iron atoms. All right? None of them are actually going to be 55.847. They're going to be very close to whole numbers, either 55, 56, 57, 58, or 54, 53, 52, that sort of thing. All right? And the natural abundance of those different kinds of iron atoms will differ, or not of kinds of a given element will differ, right? Some elements have only 2 different kinds of isotopes. Some have very many different kinds of isotopes. Some have many different kinds but only predominate 1 or 2 different kinds of isotopes. Okay? Or sorry, I didn't introduce to you the word isotope, but that's what we call these different kinds of atoms that have the same number of protons but different number of neutrons. So for example, carbon-12, carbon-13, and carbon-14 are examples of isotopes. So when you refer to an isotope, you're really saying this isotope here of carbon-14, and you're pointing out the fact that it differs from other isotopes, other atoms of carbon that have different numbers of neutrons in them. All right? So, that is our term isotope. Different number of neutrons, but the same number of protons. Chemically, isotopes are essentially identical. We don't notice anything different about them chemically. These isotopes are valuable, and we do chemistry that takes advantage of the knowledge of the natural concentration of these isotopes, like carbon dating. I don't know if you've heard of carbon dating, but carbon dating is essentially a method that looks at the ratio of carbon-14 to the other isotopes, and from that ratio it can tell you how long the material has been alive. Now that's because carbon-12 and carbon-13 are naturally abundant in the atmosphere and in the world, and as carbon-13 reaches the upper atmosphere, it's radiated with really high amounts of energy from the sun, which can actually convert it to carbon-14. That carbon-14, in the form of carbon dioxide usually, floats down, gets incorporated a natural amount into anything that is either undergoing photosynthesis or eating something that's undergoing photosynthesis, or eating something that ate something that's undergoing photosynthesis. Or in other words, if we eat plants or vegetables, and we fruit or vegetables, and we consume meat, then we're constantly upgrading our concentration, or constantly maintaining our concentration of carbon-14. Now, as soon as we die, that concentration will begin to drop, because we're not taking in carbon. We don't take in carbon when we breathe, right? So, and plants take in carbon from when they undergo photosynthesis, right? So you can tell, for example, how long a plant has been dead, or how long a person has been dead. Now, we don't think much about how long a plant has been dead. Why would we care to do that? Well, you can age material like a cotton shirt, a shirt that was made of something that was living at one point, like cotton or wool, will be able to undergo, it'll tell you how long this plant was, how long ago the plant had died that it was made from. And so you can do carbon-14 dating on systems and tell how long they've been alive, right? There are other isotopic dating methods that help us know how long different rocks and minerals have been on the Earth, or in the universe, or in the solar system, right? And so this is a way that we can tell the age of the solar system, of the universe, of the oldest rocks that we have on Earth. So it's a very valuable tool. Okay, so here is another example of our atomic notation that we have, our way to represent elements. Looking at this atom right here, this is helium, He. Can you tell me how many protons are in the atom, or the nucleus of this helium atom?
Yeah, 4.
Okay. Protons are actually just this
I'm
number
sorry.
down here.
There
Right?
were, yeah. So 2 then.
2. 2 protons. Very good. Now what about neutrons? How many neutrons?
2.
2. Very good. 2 protons, 2 neutrons. This 4 is telling us the sum of those 2. All right? Very
Right.
good. So, here's a page for us to practice. Can you look at your periodic table and find out how many protons are in an atom of cobalt-60? How many protons are in an atom of cobalt-60?
Okay. 27.
Very good. 27 protons in an atom of cobalt-60. All right. How many neutrons?
33.
33 neutrons. Very good. Excellent. Now, we haven't talked recently about number of electrons, but a long time ago we said that if an atom is uncharged, that means it has the same number of protons as electrons. So how many electrons is this cobalt-60 species going to have?
27.
27.
If it's uncharged.
It's right. It's uncharged. Now, we'll talk about this in a few slides, but the charge would be up here to the superscript, to the right of the element. So let me show you an example. If this was carbon-14 here, and I wanted to show you that it had fewer electrons, I would say it has a positive charge. That means it has one more proton than it does electrons. If I wanted to show that it had 2 more protons than it has electrons, I would put a +2 charge there. If I wanted to show that this carbon-14 has 1 more electron than it has protons, I would put a negative charge there. All right, so bromine-81. How many protons, neutrons, and electrons for bromine-81? Bromine is underneath number 17.
Oh, okay. Thank you. So 35 protons.
Very good.
And then 46 neutrons.
Very good. 46 neutrons.
And then it would be 35 electrons.
35 electrons. Very good. Now, given this information, 29 protons, 36 neutrons, 29 electrons, what kind of symbol are we talking about here? What kind of element is this?
So it's I'll tell you in just a minute. Okay, so that's copper.
Okay, copper. And what would we call it? Would we call it copper 29, copper 36? What would we call it?
We would call it copper 65.
Very good. Copper 65. Excellent. Okay, good job. So, here's another one you could practice. I don't think we'll take the time to do this one, but for any of those at home that want to, you push pause and then find the answer. Here's one more that you could practice. Push pause and try to find the answer if you want to. I'm going to show it to you now. Okay? we're going to spend some time trying to answer this one here, which is a little bit more complicated, has a little bit more information in it, so we need to talk more about it. All right? In this problem, they tell us that naturally occurring chlorine is a mixture of two isotopes. It's chlorine 35 and chlorine 37. 75.77% of the atoms are chlorine 35, whereas 24.23% are chlorine 37. And the measured mass of chlorine 35 is 34.9689, and that of chlorine 37 is 36.9659. So we want to calculate the average atomic mass of a chlorine atom. Okay? So, if we want to do this, we need to think about how the average mass of an atom is identified. Okay? So, let's say I have a hat. All right, here's my hat. And inside this hat, I have a bunch of chlorine atoms. And I pull them out one at a time and check their masses, the masses of these chlorine atoms. All right? Because what I want to do is I want to find the average mass of the chlorine atom. All right? How would I do that? What would I do? What would I do when I pull the atom out and check its mass? How would I find the average if I'm going to keep pulling them out and checking masses of the atoms?
So if you have pulled 10 of those out, you would add up the total number of the masses and then divide by 10 to get the average.
Very good. Excellent. That's how I find the average mass. Perfect. So in this experiment, they were pulling out atoms, and let's say if they pulled out 100 atoms, 75.77 of those atoms, that's what the 75.77% had a mass of 35, or 34.9689. And 24.23% had a mass of the 36.9659. So how can we, instead of making a list here of the 35, let's see, the second one was 35, and the next one I pull out 37, and the next one I pull out 35 again, and the next one's a 37, and then the next one a 35, right? Instead of making this long list, which is fine, but would take a really long time if I wanted to write down 35 75 times, and then the 37 24 times, and then add it up in the calculator, right? It would be wiser to just count how many 35s there were and multiply 35 by that value, right? And then add that to the 37s times how many times that one came up, all right? So in a sense, what we do then is we take our 35, our mass, which for 35 is the 34.9689. We multiply it by the percentage. Now, what percentage is the 35? Can you see that?
75, yeah, 75.77%.
That's right, 75.77. So out of the 100 that we pull out of the hat, 75.77. Now I add that to what?
You add that to the mass of 34. No, I'm sorry, I'm looking at the wrong one. Yeah, thank you. 36.9659 times 24.23.
Very good. Now what do I divide all that by?
2.
No, I didn't pull
4.
2. No. This 75.77 is my per what?
Okay.
Per what? What does this little symbol mean?
Oh, per, I'm sorry, where's the somewhat, well, percent.
Percent.
So
That's right. For every what?
that's 100.
For every 100. So I divide it by 100. And that will equal my average mass. Okay?
Okay.
So 75.77% times the mass of the 35 plus the 24.23% times the mass of the 37 divided by 100. We put that in our calculator and we get 35.45. Okay? Hopefully doing that math isn't that big of a deal for you. You just do the multiplications here and here, add them together, and then divide by the 100. And that's how we get our mass. Very good. Now, we want to make sure everybody understands why we didn't just divide that by 2, right? Because
Right.
it feels like, wait a second, there was only 2 elements. It was either a 35 or a 37. Why didn't we just divide by 2? We're not dividing it by how many different kinds of elements there were, different kinds of isotopes. What we're doing is we're drawing all of our isotopes out, and we're finding the average by adding them all together and dividing by how many we took a look at. Okay? So we got 75.77%, right? Clearly, I mean, you couldn't have drawn 75 times and gotten a percentage of 70, or 100 times and gotten 75.77, right? They had to draw 10,000 things out of there and 10,000 atoms, and then found that 7,577 out of the 10,000 were chlorine 35, but then they express it as a percentage out of every 100, and that's how we get the fraction there. Okay. Here's another one. Now in this one here, they tell us what the average is. They tell us that the average is 155.5, but they want to know what the mass of one of the isotopes is. Okay? So let's see if we can figure out how to do this. We have to set it up the same way. We have the mass, the average mass this time given to us, 155.5, right? And from the information provided, how would we set this up?
So we would, so underneath, we would go ahead and use 100 there.
Yeah, we would be dividing by 100. Very good.
Okay. And then the first is, so we have 56.5.
Yeah, 56.5%.
Yeah. And that has a mass of, so we would, of 152.3. So that would, we would multiply that, right?
Very good. And then what do we add that to?
And then we're going to add it to a mass of 155.5.
No,
that's our answer.
That's our average, right?
That's our average, right? So it's going to be
we don't know the mass, do
X.
we? Yeah, that's our unknown, right? Our X, our mass.
Right.
We don't know. Good.
Right.
Do we know the percentage of it?
And that's what I was looking for. I guess we don't, do we?
But it says that there's only 2 isotopes. There are 2 isotopes of this element.
Okay. Okay. So then it would be 56.5, right?
Yeah, we would take the 56.5, or we take 100 and subtract from it the 56.5. Right? And that's 43.5. All right? So you see where I got...
see. Yeah.
Okay, great.
Yeah, I did.
Excellent. Now to solve for the x here, we'd have to multiply both sides by 100, and then we'd have to subtract the product of this, and then divide by our 43.5, and if you do that in your calculator, it should get 159.7. So make sure you know how to do that with your calculator. Make sure you practice that. Don't just skip it because we gave you the answer. If you can't get 159.7, keep practicing. It's important that you have a good calculator. If you don't need to have this specific one, but you don't want to use your phone. You want to have a different calculator that you can dedicate to doing calculations and that you can become familiar with. And that way, what it does is when it comes time that you really need an answer, you're not just calling on some weird calculator somewhere that you've never seen before or going on the internet and trying to calculate numbers. You want to become familiar with a calculator so that the calculations component is easy. It's not the hard part, because you don't want to spend brain power trying to figure out how to use your calculator too much, or every single time you come into a new calculator, right? So we'll have to make sure we find a good calculator for everybody. All right, here's another one. This one doesn't require a calculator, but it does require an understanding of what the terms mean, isotopes and so forth. So if an element has an atomic mass of 15.987, a theoretical element, 15.987, the mass of one of the isotopes, X, is 15, and the mass of the other is 16. What does that mean about the natural abundance of the different isotopes? So again, the 15.987 is the average. Now, they don't tell us how many different atoms had the mass of 15 and how many different atoms had the mass of 16. But we can kind of guess that. Actually, we can actually mathematically identify it. But we have some information. We can know that without even actually doing any calculations, because the information provided is the 15.987, right? It says that's the average. So what does that tell us about the average abundance, or the abundance of the 16 and the 15 isotopes? Would the abundance of X be the same as that of Y? Or would the abundance of X, the lighter one, be more than that of Y? Or would the abundance of X, the lighter one, be less than that of Y?
Less.
Less, that's right. The abundance of X would be less than that of Y, and that's why the average is more towards that of the Y isotope. What if X and Y were exactly the same percentage? What would our average mass be then?
I'm sorry, say that again.
If our abundance of the 15 isotope X mass of 15 and the Y mass of 16, if they were 50% of both of those exactly the same, what would our average mass be?
Um,
Well, let's do it in the on paper here.
okay.
If
Yeah.
I had 50% 15 plus 50% 16, divide that by out of every 100 that I'm looking at, right? 50 times 15, 50 times 16. So I'm going to add I'm going to add 750 to 800. And then I'm going to divide by my 100. So it's exactly 15.5. Does that make sense?
Yeah.
Because if they're half 15 and half 16, then really all you have to do is take the average of 15 and 16, and it's 15 and a half, right? Okay, very good. So let's talk a little bit about the history of the periodic table. Dmitri Mendeleev is kind of a popular figure, especially in Russia. They love to let everybody know that he was the one who discovered or organized, right, the periodic table. Now, there were a lot of people that were trying to do this because it was pretty clear early on that a table that had all of the elements organized was going to help us compare the elements to each other. Because when they're in the same column, they seem to have similar properties. And even elements in the same row they'll have different trends that you can kind of follow and predict then what will happen when different elements are combined. So Dmitry Mendeleev gradually figured out how these elements kind of could be combined in a table, and he then began to be able to predict, because he identified what we call periodicity, which means that different periods or different columns have similar properties up and down. And as you move down the column, the property will change. For example, reactivity. Chemicals generally become more reactive as we move down a column. Okay? So, the periodic table is more than just a way to look at the number of protons and electrons. It's a way to predict the new kinds of compounds that can be made, and the new kinds of properties that those compounds will have. All right? So, periodicity is across. That's our periods are going our rows this way. But we arrange we talk about our periodic table in terms of rows or columns, and columns can also be identified as groups or even families, all right? Families. And the noble gases here, the last family of elements on the far right row, is probably the most popular family in the periodic table, okay? But we'll introduce to you a handful of others, a few other families as well. The periodic table can be broken up into what we call the representative elements. The representative elements are the first two columns and then the last six columns in our periodic table. And this was kind of the initial periodic table that Mendeleev put forth, was these 8 columns. And these 8 columns are called representative elements because they follow they follow patterns really well. So they represent certain kind of rules in chemistry that people use to understand how compounds form. So the first 2 and the last 6 are called representative elements. The separation between those 2 groups is called transition metals on our periodic table, like this. This blue section here are our transition metals, with this lower block here being called the inner transition metals. Okay? We also have, as I said, some families that are very popular, and we want to kind of remember their name a little bit. One family is what we call the alkali metals. It's this first column over here far to the left, and it contains the metals lithium, sodium, potassium. All right, I don't know if you have any familiarity with these, but I remember when I was in high school, one year somebody stole some sodium from the chemistry lab and flushed it down the toilet, and it blew up one of the toilets. Sodium is explosive when you put it in water. Lithium has a very similar property. If lithium-ion batteries, especially larger battery packs like in Tesla cars, if they get broken open and exposed to moisture, they can heat up, catch on fire, and if large battery packs like that catch on fire, the whole car will burn to the ground. And this happens frequently with Teslas, well, I mean, relatively frequently compared to other cars that don't have batteries, right? You don't just see cars lighting on fire. But don't worry, Tesla will replace the car if that happens. And there hasn't been scenarios where the fire is so fast that people are hurt. So generally this is a very slow process and probably not a reason to not buy a Tesla. But it is an example of how lithium has its precarious properties that we have to deal with. Okay? So those are our alkali metals. Oh, one thing I wanted to mention is after you mix or interact these metals with water, the resulting solution that results, the water after you're done, has a property of being alkali. Now, not everybody knows what the word alkali is. almost everybody feels like they understand what the word acidic means. Well, alkali is the opposite of acidic. And you don't have to know exactly what it means for now. We'll introduce it to you and get a good understanding of what acidic means and then also what alkali means. So that's our first row, alkali metals. First column. Our second column, alkaline earth metals. Alkaline earth metals. Very relatively reactive still, but not explosive when they interact with water. Our final two columns here are also very popular. The second to last one are called halogens, fluorine, chlorine, bromine, and iodine. And they become popular because of the reactivity trend going up and down, and we'll talk about that in the future, and also their state at room temperature, also very popular for that. And for a variety of other properties of different compounds that contain these elements. So the halogens are often referred to. And then probably most frequently referred to are our noble gases, Now, you can think of nobles as kind of like the king and queen and the royal family, and that still helps when thinking about noble gases, because most of the chemistry, if not all of the chemistry, that occurs between elements so that they can change their electron configuration to be like that of noble gases, all right? Specifically the representative elements. And we'll talk a lot about how representative elements combine to attain noble gas electron configurations. So they want to have the same number of electrons as a noble gas. Okay? Very good. The periodic table should really be formatted like this, because this is how it is separated from the different columns actually arrange themselves. But because we work with an 8.5 piece of paper, this is how we see it, right? 8.5 by 11 piece of paper fits our periodic table like this better. That staircase, do you remember from our previous classes, what does that staircase separate?
Metals from nonmetals.
Very good. Metals from nonmetals. Metals on the left, nonmetals on the right, with the notable exception of hydrogen, which is considered to be a nonmetal. However, if hydrogen is exposed to, or hydrogen in its property, or in compounds, behaves relatively similar sometimes to these elements. So it is appropriate for it to be over there as well. In old periodic tables, you'll see it over here, because it also behaves kind of like fluorine, chlorine, bromine, and iodine when it's in certain compounds. Okay, so let's see if from our conversations there, you can pick out which of the following is correct. All right, you might have to use your periodic table a little bit. It might help to get this as big as possible so that you can see this information here. Maybe it's too small to see. Maybe we bring in our periodic table and look at them one by one. Copper. Here's copper, number 29. Is that a representative element?
Yes.
All right. What were the representative elements? Do you remember?
I got that wrong. Okay.
The representative elements were actually the first two columns and the what?
That's right.
The last six.
Yeah, that's right.
Okay.
Yes.
So copper is not a representative element. Do you remember what that blue section is called? Can you read that small writing?
I don't. Oh, that's the transition. Okay.
Very good. Very good. That's the transition elements. So on our periodic table, the blue ones are our transition elements. So copper is not a representative element. How about this? Sodium is an alkaline earth metal. Alkaline earth. Was the alkaline earths the first column or the second column?
First column.
The first column was what we actually called the alkali metals. The alkali metals.
Oh, okay.
So
Alkaline earth would be the second column.
The second column, so that is not true either.
So that's not true. Okay.
How about carbon is a semi-metal? Can you find carbon on there? 6 protons.
6 protons. Okay.
Is it?
And that's.
Is it a semi-metal?
No.
Nope, it's not.
What?
Okay. What about this next one? Fluorine is a halogen. Do you remember which column were the halogens?
Okay. Yeah, that's true.
That's true. That's right. Fluorine, chlorine, bromine, and iodine are our halogens. Excellent. Okay, so let's talk a little bit more about the properties of metals. Most of us have an idea of what metals are. We interact with them every day, right? Somehow. However, a lot of the metals that we interact with are actually combinations of different elemental metals to make alloys. If you have a metal that by itself is just one kind of element, like I mentioned previously, if I take my ring and if I were to buy 24 karat gold, which means pure gold, the ring would be very easy to bend. And so they don't sell a lot of 24 karat or pure gold. Here's a video of somebody using a chisel to break apart some sodium metal. Looks like brie cheese. They just kind of can work it. It's really what we call malleable, easy to kind of break up. Not terribly easy, but pure metals have this malleability, that property. Okay, they're also shiny in general, but you can see the surface of this sodium, it has a white haze on it, kind of like brie cheese. And the reason is because the sodium is very reactive. It reacts with the moisture in the air, the oxygen in the air, and the result is a new material on the surface. Okay. You have to keep something like this, a metal or any chemical that's hygroscopic, or that reacts with water, in a desiccator like this. And the desiccator has material at the bottom which will absorb the moisture away to keep the moisture out of contact with the material. All right, we saw this before as well. Dropping some sodium into water. We're going to drop another one. This time it's at night.
Good snap.
Put a little bit of sodium into some water. All right. Does that remind you of anything? 4th of July? Kind of looks like fireworks, right? So a lot of fireworks will contain either sodium or potassium because of the reactivity
150 grams.
that they have, right?
Oh, perfect. Excellent.
Well, I guess I shouldn't necessarily say that, but you can get those colors from sodium, that color that we just saw of
Good
the
snap.
deposit here. That kind of orangish, yellowish glow, yellow-orange glow, comes from sodium metal. And in fact, older light bulbs, older street lamps used to be made of this color. Or on the big island of Hawaii, they still use sodium street lamps with the goal of trying to keep down the interference for the telescopes up on the mountains. All right? Okay. So, metals conduct electricity. They conduct heat. Generally, they're solid. Mercury is the only one that is solid at room temperature. You can make any of them liquid or gas by heating them up. But mercury is an example, or an element that is liquid at room temperature, a metal that's liquid at room temperature. So it's kind of an interesting scenario there. We also mentioned about reactivity, putting sodium in water. That's what we just saw. Lithium in water, we talked about that. As you go down the column, you increase the reactivity for the alkali metals. And we have another video here of somebody putting these two other elements here, rubidium and cesium, into water. So we're going to watch that here.
Back and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
Yes! Wow. That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does.
All right. So we see a good kind of example there of increasing reactivity as we move down our alkali metals, our column for our alkali metals, or our family of alkali metals. All right. Now, nonmetals. Nonmetals, we don't interact with a lot of nonmetals in science, or sorry, in the everyday world either. Again, most of what we interact with is compounds that contain nonmetals. We always are breathing oxygen and nitrogen. Those are nonmetals. So those are some examples of nonmetals that are gaseous. Most are either solids or gas, with one, bromine being a liquid at room temperature. All right. Nonmetals will react with metals to form what we call ionic compounds. And we've talked about that before, ionic compounds. And we said that we could identify an ionic compound because it is a compound that contained a metal, right? And that was to distinguish it from molecular compounds, which are compounds that only contain nonmetals. Nonmetals are not malleable, ductile like metals. They shatter. You can think of kind of hitting one with a hammer and kind of going everywhere type thing. All right, if it was in a solid form. Okay, metalloids. A little bit about metalloids. It is that, in this case, green staircase. Everything along that green staircase there, not aluminum. Aluminum is not a metalloid, it's a metal. But these properties, or the properties of these elements, is that they can either behave like a metal under some conditions or behave like a non-metal under some conditions. And silicon, this specific property allowed people to begin to store data, right? The data from computers was stored in the form of small pieces or small sections of a silicon wafer being identified as with a charge, 1, or without a charge, 0. And that binary language and the ability to store a piece of material with that binary language resulted in what we have in terms of our computational storage. Okay. Now, we talked about how ionic compounds are compounds where a metal and a non-metal come together, but we haven't really talked about why they want to come together too much. We mentioned it briefly, but I want to have a conversation about why they come together. Why do metals and nonmetals come together to form ionic compounds? And this is pretty much the reason, right? If we look at our periodic table, we look at the elements like our noble gases, helium, neon, argon, and we look at the number of electrons that they have. Elements that are representative elements that are not noble gases, like chlorine, for example, are only one electron away from having an electron configuration similar to that of argon. Okay? And you can think of argon, I'm going to draw argon here and just kind of anthropomorphize, I can't say it right now. I'm going to pretend like argon's a little person. He's the king, right? He's a noble gas. He's very happy because of his abilities, right? He has the perfect number of electrons, the magic number of electrons, and protons. But that makes everybody else kind of mad. Specifically, chlorine in this case. Not happy, right? Chlorine does not have the number of electrons that argon has. It has 17 electrons, right? Our periodic table shows us that it has 17. And if it had 18, then it could have more similar properties in terms of stabilizing itself to that of argon. Another element that is also unhappy with its existence, right? And when we talk about unhappiness, these things aren't really people and have unhappiness, but their activity, their stability, they are not stable as elements, right? So what are we going to do to stabilize our sodium and our chlorine? Well, can you give me a guess why sodium might be unhappy? It's element number 11.
Oh, okay. Thank you. Oh, yeah. Okay. That's right. I forgot. Why sodium would be unhappy?
Why would sodium be unhappy?
It's
well, why was
too reactive.
why was chlorine unhappy? Why is it so reactive? What did I just say?
Well, it was unstable.
It only has 17 electrons.
17, yeah.
And if it had 18, it could stabilize itself. So it needs more electrons, right? Sodium has 11 electrons. How is that in terms of in comparison to the noble gases?
Well, it's too much.
It's too much. It has just one too many. You could also say, well, it could gain 7 and become like argon, but it's easier for it to just lose 1 and have a noble gas electron configuration of neon. So what happens is sodium and chlorine react. They react. They react in such a way that sodium will give an electron to chlorine. And when sodium gives an electron to chlorine, it gets a positive charge. Chlorine gets a negative charge because it gains that extra electron. And the resulting species there, which we call, and this is a new word, we call them ions. Ions are atoms that have different numbers of protons than electrons. And the result is what we call an ionic compound. Ionic compound. So ionic compounds are really compounds that are made of ions. Now we said we could recognize an ionic compound early on by whether or not it had a metal in it, and that's reasonably good definition. But a better definition of an ionic compound is a compound made of ions. Now we didn't know what ions meant previously, so we didn't know how to say that. But now we do. Very good. So, let's look at this as a quick review. An atom of sodium. How many protons does an atom of sodium have?
Oh, I'm sorry. Is that a
Na. How many protons? It's underneath number 3.
11?
11. 11 protons. How about how many electrons does this atom of sodium have? Has the same number,
11.
right? That's right.
Oh, yeah.
11 electrons. 11 protons and 11 electrons. Now, over here, with the positive charge, it lost what? What did it give up to get a positive charge?
Electron.
It gave up an electron. So, how many protons does it have now? And how many electrons does it have?
So he has 10 electrons.
10 electrons.
Still has 11 protons.
Still has 11 protons. And that's why we get this positive charge. It has more protons than it has electrons. Right?
Right.
So let's look at this chloride ion. What's the charge on, or why does the chloride ion have a negative charge? How many protons and how many electrons does it have? How many electrons and protons are on an atom of chlorine, or an ion of chlorine? This chlorine ion.
So we have 17 protons.
17 protons, that's what the periodic table tells us.
And then we're going to have 18 electrons.
18 electrons. Very good. Excellent job. Now, people sometimes forget what the positive sign means. They think positive. Oh, somebody has added electrons, so it must have more electrons. But the positive sign is showing that there's a resulting positive charge because of the difference between the number of protons and electrons. So it means that there's one fewer electron. All right. Very good job. We'll see you later.
Okay.